So I said the Ackermann function was an example of a function that can't be made into an iterative function, but all recursive functions can be made into iterative functions. It's simply that the Ackermann function is not primitive recursive, which just means that we can't make into an iterative function whose loops we know the bound of before we actually execute it. So we don't know the bound a priori before we actually execute that. All right, so that's just the clarification. Then we were looking at examples of recursive functions. We looked at Euclid's algorithm for finding a greatest common divisor. We saw that it does indeed work. And the implementation that we have here, well, it does one thing extra, right? It decides on which version of GCD to call, or rather which arguments to pass, based on whether A is larger than B or not, so that we don't have that situation where when we looked at our 15 and our 12, because the 12 is smaller than 15, 12 mod 15 would just have made us do another recursive call with it swapped, with it now being 12 and 15 instead of 15 and 12. Coston simply looks at that and allows us to not have to make an additional recursive call where no work is done. But effectively, it's the same as the definition that we have there that we actually looked at an example of. All right. Another example that we should be familiar with is the idea of a factorial function. That factorial is simply, factorial for any integer would be that integer multiplied by all the positive integers smaller than it. So the factorial of 2 would be 2 multiplied by 1, which is 2. Factorial of 3 would be 3 multiplied by 2 multiplied by 1, which is 6, and so on. And so the factorial of n would simply then be n multiplied by n minus 1 multiplied by n minus 2, all the way up to 1. Right? By definition, the factorial of 0 is taken to be 1. And so we see for our implementation, our base case or our basic case would then be if n is equal to 0, we return 1. Then for our recursive call, we multiply the current n by whatever will be returned from a recursive call to factorial n minus 1. So we are moving towards, right? This function is true for all integers, and so just all positive integers. So we are moving towards that base case of 0 because we're subtracting 1 each time. So regardless of what n is, we will eventually get to that base case of 0. That will then return 1. That'll be multiplied by, well, 1, which will then return to the calling method, which should have been 2, which will then multiply it with 2, and so on until we get back to the original method, which multiplies it with n, and the answer will then be the factorial of that given integer n. Right. So that we should be familiar with, and now we see that we can easily create a short recursive function that does exactly that. So what have we learned? We have to have a base case. It actually has to do something. It has to return some value based on our parameters. And so in that base case, we should not be doing a recursive call. We should actually be returning a value based on our parameters. We can have more than one base case. So it could be a switch statement, and we have several different cases, or we could just have a more complex conditional statement. But one of those has to be reached from our recursive calls. All right, so every possible chain of recursive calls must eventually reach this base case. And similarly for our recursive calls, well, it's a recursive method. So somewhere within our method, we have to actually call that method recursively. There can be more than one recursive call, as in we can have a conditional statement there, and based on that, make a different recursive call. But it should be defined, each one has to be defined in such a way that eventually each of those recursive calls will move towards our base case. If not, then we'll simply get a function that iterates or that calls itself over and over and over an infinite number of times and never gets to that base case. All right, and that makes sense. So here is a visualization of a recursive method or recursive recursion trace of a recursive method with a particular argument. So here we have recursive factorial. We call it with an argument of 4. It will then call another instance of itself with the argument 3. That still doesn't qualify for our base case. It calls itself again with an argument of 2, and again the argument of 1, and finally with the argument of 0, which does satisfy our base case. So that is the first one to actually return a particular value. It returns 1, which is returned to recursive factorial 1 and multiplied by 1. That returns to the calling method with the answer of 1, which multiplies by 2, returns to the calling method and multiplies that by 3, and finally returns to the initial method, multiplies it by 4, and we get 24 as our final answer. So, easy question to ask. We give you a recursive function and ask you to draw a recursion trace of that. What you'll do is for each instance of the method, you will draw a little box that represents that instance with a particular argument. You'll then have an arrow that calls to the next instance that's created with the recursive call, all the way down to a base case, and then show arrows that are returning values to those calling methods. How do you store the final answer? However you wish. Perhaps you want to use this in an expression. Perhaps you want to store this in a variable. You see that even the very first call to this recursive method has to be from some other method, right? You will actually use this method to do something. Was the correct word for you to reach the base case and then return the values to the calling method? Is it unwinding the base case? Some text may use that. This one certainly does not. If we're to visualize what this actually looks like within our machine, that we have some method, some piece of code that's currently in memory that is being executed. When it calls this method, then an instance is created, and that's put on our stack. It is now in control. It executes until it gets to its recursive call. A new instance is created, that's put on the stack. At some point, one returns, is popped off, and returns controls the one before it. So you can think of it drilling down back to the initial method that called it, but that's not the terminology used with the text that we use. All right, now we want to classify recursion according to the number of recursive calls that are within our recursive method. We have linear recursion, and we have a specific type of that we call tail recursion. Then we'll look at binary recursion and multiple recursion. All right, the names are pretty straightforward. Linear recursion simply means that there's a single recursive call that is executed each time the method is called, except of course if we qualify for our base case. So with linear recursion, we would have our test for our base case, right? We begin with that test. There needs to be at least one so that we can actually fall into that base case when we eventually get to it. And each possible chain of recursive calls, as we said before, must move towards that and eventually reach our base case. All right. Then we will recur once, and that's what makes it linear recursion. There may be several different options, but we'll only make a single recursive call within our method. So you perform that single recursive call. Again, it may have some test. It may be a branching statement that depends on some particular values that we're looking at, where we choose from several different options of statements to execute, but they will all make a single recursive call to this method. Otherwise, it isn't linear recursion. All right. And again, with all recursive methods, we need to define it in such a way that we're moving towards our base case, or simply execute indefinitely. Here we have an example of a linear sum. So we are, and in fact, we did something similar for last week's prac. You recall you had to create an array of occurrences of particular characters in the English alphabet, and then you had to sum those all up. So this is an algorithm that could do that for us. We have an array A of integers, and we'd like to sum up all the numbers within that array. Okay, we have a second parameter n, and we see that this is actually useful for what we want to do. So we have two parameters, A, which is an integer array, and an integer n. It doesn't have to be equal to 1, it should be greater than or equal to, I'll change that, such that A has at least n elements. So we'd like to count up the n elements within A. A can have more elements than n. If we wanted to count up all of A, then we would simply set n to be, well, the length of A, the number of elements within A. All right, and it should output to us the sum of all the integers, or the first n integers within A. So our base case is if n is equal to 1, then we return A0. And that makes sense. If we simply want to sum up from the first element up to the first one, then we simply return that first element. Done. Then for our recursive call, we have to make our problem smaller in such a way that it moves towards the base case. So we call linear sum again with a, but now with the second parameter of an argument of n minus 1. So now call linear sum to calculate the sum of all the integers within this array from 0 up to n minus 1 this time, right? Or the first n minus 1 integers, not the n integers. Eventually, those calls will have an argument of n being equal to 2, and so n minus 1, which is 1, is called, and that'll enter our base case. Then whatever is returned, we add to that the n minus 1th element, which is a n minus 1, right? Or the nth element, which is that. What is the efficiency of this compared to using a loop? All right, as we said, this uses a little more space. So if we could change this into a loop, then it would be more efficient. But oftentimes you find that the recursive implementation is easier to understand. So it can be more elegant, even if it isn't as efficient. All right, and in fact, in cases like the Ackermann function, we don't know how many iterations of a particular loop is going to happen, so it's not convenient to use an iterative statement for that. All right, so this can work. Whatever the linear sum for n minus 1 elements gives me, I simply add to that the nth element. That makes sense, that'll give me the sum. Eventually, I'll call this function with n equal to 1, and that will return a0 as that sum. Add to that a1, and that'll be up to the second element, so on and so forth, until we get to n. All right, and so this is what a recursion test looks like. Okay, if you're not answering a question, please make sure that your mic is muted. We're going to give that feedback. All right, so this is what it would look like if we'd called linear sum with an array A. All right, A isn't depicted here, but A simply has the values 4, 3, 6, 2, and 5 in its first 5 elements, and we want to sum up those 5 elements. So we see that linear sum A5 calls linear sum now with the second argument of 4. Again, that calls linear sum A3, which calls linear sum A2, which calls linear sum A1. Now that n is 1, we simply return the first element of A, so that's A0, which is 4. That is returned to the calling function, which adds to that A1, and it does that until we get to the initial function that called it. That's A5. That calculates the entire sum of 20 and returns that to the calling function that first called the method linear sum. All right, and that should be correct. If we were to add 4, 3, 6, 2, and 5, we'll end up with that 20. How can we use recursions on data structure? All right, there's actually a question asked yesterday. I think Walker asked it about trees, and the answer I gave was actually more for general graphs, that yes, there are some algorithms that use like depth first search and breadth first search that use recursive algorithms. But where we have a data structure like a tree, which can actually be defined recursively, that a tree, we have this root node and its children are all trees themselves, then almost all our methods can use recursion. And even methods to calculate the attributes like the height or the depth, the recursive functions to do that are a lot simpler, a lot more elegant than the iterative ones. So we often use it with data structures that lend themselves well to recursion, like a tree. Then, was the slide of code to answer the one question from Newport's exercise 1.4? Irish Java method that takes an integer n, returns some ballpark integers less than or equal to n? Yes, that would answer that question. All right, but there's more than one way to do this. Okay, no, there's not that. Here is another method that allows us to reverse the order of elements in an array. So here we pass an array A and 2 indices I and j, and what it'll do is it'll swap all the elements between those indices I and j. So the output should be the reversal of the elements in A, starting at index I and ending at index j. So what do we actually do? If I is less than j, so let's imagine that logically I is the lower index and j is the higher one. So we should have that I should always be less than j. If that's true, then we swap the contents of AI and AJ, right? So if I was 0, if it was the very first element, and J was at length -1, the very last element, then this would swap those two elements. Then it would call reverse array again on A, but with I incremented 1, so now we've moved to the second element of our array, and J decremented by 1. So J now the second last element. Then it would do that swap again, certainly, right? And it would do this over and over and over, each time swapping pairs, getting closer and closer to the middle, until, and this is interesting because our base case isn't actually explicitly written here, because our base case will do nothing, right? It'll simply skip this branching statement and return. And so how do we get to that base case? Either it is an array that has an odd number of elements, and so eventually I equals J, and so we shouldn't swap anything. That single element can't be swapped, right? It's in the middle, so there's nothing to swap it with, and so we then return. Or it was an even number of elements. Eventually, I and J are right next to each other. They swap, and then the method is called with now I being greater than J, because let's say I was 4 and J was 5. I gets incremented to 5, J gets decremented to 4, and so now this is not valid. And so our base case is actually to do nothing. Whereas for the recursive call, if that isn't true, then we keep swapping those pairs of elements. All right. Even if it wasn't the entire array, let's say I was somewhere higher up and J was somewhere lower down, as long as I is less than J, we will swap pairwise until we get to the point where either I is equal to J if it was an odd number of elements, or I is greater than J if it was an even number, and then we do nothing and return that array. All right. And in fact, this works as a procedure rather than a function, because arrays are passed by reference, simply does the operations and eventually returns. And we have that A has its elements swapped between the indices I and J. So we saw some interesting things. For our factorial function, we had a single parameter n, and each time we called our function recursively, we would reduce that size of n to move towards our base case. For the other methods that we looked at, for the linear sum and for this reverse array, why is it that we chose to include more parameters? So why is it we chose to allow more arguments to be sent each time that we call this method? Well, it's more convenient, right? It's important for us to be able to choose our parameters in such a way that we're able to move towards that base case. And for our linear sum or this reversing of the array, we could have instead created a clone of that array and copied the elements between I plus 1 and J minus 1, swap those two, and then did the recursive call with the smaller array, and each time do a recursive call with a new small array each time. Would that be efficient? No, because we're wasting a lot of space. Even for the linear sum, we could, instead of passing n, simply say we want the sum of the entire array, and then to get a smaller and smaller problem that moves towards a single element, we create a copy each time and recursively call it with one less element. So if the array of size n, we can call linear sum with a new array that has everything up to n minus 1. So on until we get to a single element array. It would still work, but that's not half as efficient, because each time we're creating a new instance of an array or brand new array that's simply smaller and moving towards that. Whereas if we pass these indices in reverse array, or that single n, which represents the number of elements from the beginning of the array, it allows us to be able to move towards that base case a lot more conveniently. All right, so we should do it in such a way to facilitate the recursion that we're doing to help us move towards that base case. So tail recursion is a type of linear recursion that has the recursive statement as the last statement to be executed. So tail recursion occurs when a linear recursive method makes its recursive call as its last step. Our array reversal method is an example of that. And in fact, our linear sum as well could be an example of that. Such methods can be easily converted to non-recursive, so to iterative methods, which does save some resources. So that was the question that was given earlier, which is more efficient, and certainly be the iterative one, because we're not creating a new instance of the method each time that we call it. And with these, when you have tail recursion, that you're simply doing one thing at the end, the very last thing you're doing is that recursive call, you can replace that with a loop. So we look at an example of that. We replace what we had there where we were recursively calling it a with I plus 1 and j minus 1. Instead, we do that incrementing and decrementing within a loop, and we have the swapping happening iteratively as those values of I and j change. So we do the first swap, then increment I and j. Instead of calling the method again at those new indices, we simply loop our while loop again. So we execute it again with those new values of I and j, as long as I and j are such that I is smaller than j. When we get to that condition where they're either equal or I is greater than j, our while loop stops its execution, and we then return. So this works, it does the exact same thing, and it will use fewer resources because it just iterates this loop over and over again instead of creating a new instance of the method and using more space. So this is, all right, so binary recursion is simply where we have more than one recursive call. So linear recursion said that those in any execution of that method, there may be a branching statement, so an if statement or some type of switch statement that has different recursive calls that could be made, but only one of them will be executed. If instead now we have more than a single recursive call being made, and in particular two of them, then that would be binary recursion. So here we can solve the same problem we had before of counting up the numbers in an array over a certain interval. But now instead of simply doing a recursive call and adding that smaller sum to the last element, we could cut the array in half. So divide our problem into two halves and call binary sum on each of those halves. All right. So again, we have I being the element at which we want to, in fact, that doesn't require it here. We're saying a I up to n. That makes sense. And then, oh yes, okay, the addition is correct there. So we first have I as our starting index and n the number of integers that we want to count up. We call binary sum with I up to from I and the next n over 2 elements. Then from I plus n over 2, so just after the last index that we called the first binary sum on, up to, well, add n over 2 on that, and you end up with I plus n, which is where we wanted to end to begin with. So each time we're splitting our array in half and recursively calling the method on that. What is our base case? Well, if n is equal to 1, as in we're starting at I and we want to add just one element, then we simply return the element at I. So what would that look like? We can't really use that same recursion trace that we had before because we don't have a single chain of recursive calls. Instead, now each time that the method is called, two instances are created. There are two recursive calls. And so this would look like this. If we wanted to sum up the 8 elements from index 0, so that would be all the elements from index 0 up to index 7, we'll break our array in half. We'll call the method with 0 up to 4, and also another instance of it with from the 4th element and the next 4. So that would be up to 7, up to index 7. Each of those will then recursively call. So let's look at the left branch. 0, 4 breaks up its array into 2, 1 from index 0 and the next 2, or rather 1 from index 0 counting up 2 elements, so that is 0 and 1. The next from index 2 and adding up 2 elements, so that would be 2 and 3. Each of those then breaks it up. Again, our left branch 0, 2 calls the method of 0, 1, and 1, 1. And those are single elements, right? From 0, counting up one element, and from 1, counting up a single element. Both of those simply return the element at their first index. So the first on the left branch returns a 0, the other returns a 1. Then the sum of those two becomes our 0, 2. Each of the other branches doing the same thing. Then 0, 2, and 2, 2 together are added to make 0, 4. At the end, 0, 4, and 4, 4 are added to 0, 8. How does this compare to our linear sum? Can we have an interesting question? Wouldn't it be problematic if the calls didn't return at the same time? Well, the first question is, are these being executed at the same time? Yes, they are. All right, so already there you are assuming that we have a machine that's able to execute more than one calculation at the exact same time. So whether they are or aren't really depends on the machine that this code is executed on. And in fact, if we're using Java, it also depends on how Java accesses the hardware within that. We know with virtualization that we can actually offer up less than the resources that the machine has. All right. You're all correct and you're all incorrect because it's relative, or rather it depends. It depends on the machine that we're executing on. So if this is a serial machine, only has one CPU, doesn't have hyperthreading, then what would happen is that each time there's these two recursive calls, the machine will make one of those calls, wait till that returns, then make the other call, wait till that returns, add them up and return. So with first, let's say it always lets the first one execute first. So 08 would then call 04, which would call 02, which would call 01. That returns A0. Then it calls 11, which returns A1. It adds those together. It then returns that to 04. 04 now calls 22, which calls 21, which returns A2. Then it calls 31, which returns A1. It adds those together and returns that to 04. So it really depends on the machine that you're using. If instead it can execute two calculations at the same time, like most modern machines, then you'd call to instances. All right, so it can be quicker, right? The chain of calls now, instead of being length n minus 1, if we're working down our trace, they're actually log n calls. Okay, it's order log n, it's more like a log n minus 1. But in any case, the longest depth that we have is log n, because each time, remember, log n in computer science is assumed to be 2. It answers the question of how many times can we divide n by 2, and that's exactly what we're doing. We are breaking the problem in half and doing a recursive call with half the problem on each side. And a lot of problems we solve like this. It's called a divide and conquer strategy. We break it in some pieces, in some number of pieces, and then try to attack it on those smaller problems. And either we're going to a base case with a recursive call, or perhaps we have a more complex method that can deal with some smaller problems. All right. Fibonacci algorithm can also be solved using binary recursion. And for Fibonacci, to figure out the current method, to figure out the current term, we add the sum of the two previous terms. So to figure out f of 2, you add f0 and f1. Then our base cases are for 0 and 1, we simply return 1. So it'd go 1, 1, 2, and for the next one you add 2 and 1, you get 3. For the next one you add 3 and 2, you get 5, and so forth. Lends itself nicely to binary recursion. There's exactly that. If we have k equals 0 or 1, we return, okay? And in fact, in this case, we could say we either return 0 for 0 and 1 for 1, or 1 for both. The result will be the same, because we simply have then that our f2 would then be equal to 1. So we have 0, 1, 1, and then the sequence continues in the same way. Okay, 2, 3, 5, and so forth. Our recursive call simply calls the method with k minus 1 and k minus 2 and adds the sum of those. Is this sufficient? Well, actually, if we try to sum up the number of times that binary Fibonacci is called, we see that for every other number. So if we're looking at it being called with 0, that gets called just once. It being called with 1, that gets called just once. It being called on 2, it gets called twice. It doubles every 2 values. So for compare n2 to n4, it's more than double that. n2 is 2 recursive calls, n4 is 5 recursive calls. If we look at n3 and n5, n3 is 3 recursive calls, n5 is 8 recursive calls. So it's actually doubling. Yes, not doubling for each integer, but doubling for each subsequent one, so every 2. But that means it's growing at a very fast rate. and we get that nk is 2 to the power k over 2, and that's exponential. That's not great. Right? When we get back to algorithm analysis, we find that linear time is all right, polynomial time is all right, logarithmic is better than polynomial, but not as good as linear. Once we get to quadratic, cubic, exponential is like the worst we can get. Right? Granted, they differ based on the base, but it grows at a very fast rate. And so that is not a good method. It's not very efficient. And so we see that instead we could use linear recursion, where we return two terms, and then we can simply, so each time we actually calculate what are the current two terms, and we return that. So k is equal to 1. We then return 1, 0. So you can think of that as it's returning f0 and f1 as a pair. Otherwise, to figure out I and j, it calls linear Fibonacci k minus 1. So let's say k wasn't 1, k was 2. We expect that to also be, the answer to that to also be 1. So for this, what it would do is it would call Fibonacci 1, which simply returns 1, 0. Then it would return the first one plus the second one, and then the second one as the second term. So 0, 1 would become 0 plus 1, which is 1, and 1. All right, which makes sense. That is the second and third element in our Fibonacci sequence. And so now we have a fixed number of recursive calls, rather it's growing at a linear rate rather than that exponential that we had before. All right, there is one last example in the text. Is it in the new text? Maybe in the new text, but certainly in the old one, that simply shows how we could use recursion to figure out all the permutations of a sequence. I'll leave that for self-study. But if you've done any work with permutations and combinations that you guys have done first year, let's actually look at the trace rather for it. If we had a set with 3 elements A, B, and C, and wanted to figure out what are all the different permutations of A, B, and C, and we wanted to test, actually, of all the different permutations, not just our 3-length ones, so of all the different permutations we could have of A, B, and C, and we wanted to test these against some puzzle to see if they work, then we could figure out these different permutations by taking out one element from the set and recursively calling the function using that element. And we do this for every element in our function. So this puzzle solve 3 ABC would take out a single element of A, B, and C and recursively call the method each of those. That's exactly what it does. It calls it now for 2 length permutations with A taken out and does the same thing with B and with C. The next recursive call now takes another element out and concatenates that with the current element that's already out. So it makes A, B on the one side by taking out, if you just look at the left branch, puzzle solve 2A and B, C in our set. We have A, we take out either B or C, so we do recursive calls of both, and that gives us AB with C still remaining, or AC with B still remaining. Each of those then do a recursive call, but they only have one option, so it returns a single, there's only a single combination that can be created, a permutation. The one is ABC, the other is ACB. And so we see we end up with, well, if we look at the very bottom, those are all the length 3 permutations, but if we go up, we also have all the length 2 permutations, and on our first level, that ABC, all the length 1 permutations. So we could use a recursive method to figure out all the permutations of the items within a set. All right, so you can read through the example of actually how we would use these to solve a problem in the text, but the working of it is by doing such, by pulling out a particular element and recursively calling our method with all the options of elements to do that, you can end up with all the various length permutations that are possible with those items, which is pretty useful. We could use the same thing to figure out all the different binary numbers that we could have. All right, so we could do a lot with that. Could be used for probabilities with small sets. Yes, assuming that that there's the same probability of anything being chosen within that set, so that we have a normal distribution, then yes, you could use it to do that. Yes, and solving anagrams, because those are all permutations, aren't they? And then perhaps you could check that against a dictionary to see which of those permutations actually gives us a word that exists. And in fact, this would not just give you the anagram that uses all the letters, but all the combinations of letters. So even words that use some subset of the letters within the initial sequence that you were given. So quite useful. All right. Yes, okay. You shouldn't, but you could use this then to brute force different password combinations, assuming that whatever application you're trying to access would allow you to, try different numbers of or a large number of combinations within a fixed period of time. And that's actually how a lot of applications are solved that. They say each person is allowed, 5 tries within every 5 minutes. And so it slows down your machine to the point where we've already seen that just for length 3, we end up with 6 combinations, and that grows exponentially. And it actually depends not just on the length, but on the number of characters we have. Here we only have 3 characters. In English, we have 26. And so it grows very quickly. So it's powers of 26. All right. So if you'll give me a moment, whilst I display what today's assignment is, I will first upload it as I promised last time. We did sync the class list just prior at about 11 o'clock and assign those students to groups. So you should all be able to log into Eve. If you were registered by this morning, you'll see that you do have a group assignment. You'll see that you can tell who your assistant is. So you should be able to submit the practical. I should mention, although this really should not change how you perceive the practical, but that because of a concession to extend the registration up to the end of this week, the faculty has deemed it necessary to not have summative assessments within this week. And so this assessment is not a summative assessment, right? It's not to actually evaluate your knowledge, but rather to help you understand the work better. And so whilst you should submit your prac and it will be marked, that mark will not be counted towards your PCM. All right, so again, it's due today at 6 p.m. I will add the source files now under additional files. All right, just hold on. I will address the questions after I upload this. All right, so you should be able to see Prac 2. That gives you the document that we have here and additional files that has the source files. Okay, I'm just opening them up to make sure that it's all correct. Yes, good. All right, so you should be able to access that now and to actually look at that while we have this discussion. All right, someone's already decided to jump away. Lovely. How about Prac 1? Well, this wasn't decided last week, so Prac 1 still counts. What if we fail some pracs? Well, as with the other years, we're not going to take all your pracs. We take the top X and we choose X on, well, what is a representative sample? So it can't be like less than half of them, obviously. So if we do 10 pracs, it'll be used at least 7, and a number that benefits the class as a whole. So we look at the throughput for the PCM for different numbers of pracs, and we take the one that helps everybody the most. All right, so it is fair. And yes, usually we'll have a couple bonus pracs at the end of the year, which you can choose, or the end of the semester, which you can choose to do or not. But if you do, those are counted towards the marks that you have that we take the best X of. All right. The question was asked just two before that. Is it for both pracs? No, it was only decided this week. So we can't retroactively change an assessment you're already given, but it does count for this week. As I said, though, even if you're not registered, we will give a Dropbox link so you can submit it. And if you're registered by Monday, then that will be marked. But for the rest of you, you should submit, have it marked, so you can see whether you understand or not. All right, so as promised, this prac will be about single linked lists. For the application, I'll get to the questions once we've gone through it properly. So we're gonna ask you to try to remember the work that you did on object input and output. So you're going to write objects, not in text, but as objects, so serializable objects to a file, and read them from a file as well, right? That is really the only application. The rest of that program is written for you, and then you're going to implement several methods from our for our single linked list so that it adheres to the definition of a list. So recall that we said that a list has certain accessor and mutator methods. So we'll actually take a look at that list interface, and then you can go ahead and implement the methods within the single linked list. All right. And so the first two are the methods within our main file. The others are within the single linked list. Again, we have our mark sheet, and there you have the marks. It's fine, great enough that you'll be able to see where you struggled within that. All right, so let's just try and remember what it is that we're trying to do with our single linked lists. So I have a little presentation that we'll look at, and we'll go from there. All right, just before there were some questions, I wasn't able to do Prac 1 since I wasn't registered. That means that Prac 2 will count for PCM? No, it's only this one that isn't counted. All right. So we recall we spent most of our Tuesday lecture discussing single linked lists. We have nodes which store some element and a reference to the next node within our list. So here we have a list of size 3. Our first reference, we keep a reference to our first node that we call head. We keep another reference to the last node in our list that we call tail. And the tail node simply points to null. All right, so the last node has a reference, but doesn't refer to any object. If we wanted to insert after or add after a given method, how do we do that? We should pass an element that we want to add after a particular node. We'll create a new node, store that element in it. Then we want to add that element after, well, in this case, after the second element in our list. How do we do that? Well, one option would be to take the value, right, to change the value of the reference in our second node and have it now refer to the new node. Unfortunately, if we do it that way, the new node has no way of figuring out where it should now refer, because we no longer have a reference to the element that comes after that current node 2. So instead, we should first update the reference of our new node, the next reference, to whatever the node they want to add after it is next. So that reference, then update the reference of that current node to be the new node, and we now have a list, right? Because you understand that that reference in the middle there, so this reference now goes away because we have updated it. So we now have our list that includes that new node. All right. All right, so a couple of questions just to make sure. We meant to have a text file, product items, the source file. No, it won't be a text file, it'll be a binary file, and we're writing objects to that. Initially, you don't have anything. So, well, your program should handle it eloquently enough that it should simply say there isn't a file there. But when you write to a file, you should create that file, write to it, then be able to read from it and add new nodes to that particular list. All right, so I don't have to submit, I can just practice. All right, if you practice, then yes, that's enough. For you to do the prac is enough. If you want to get marks for it, so to see how well you did, then you should submit as well. Okay, the same questions being asked again and again. No, only this prac won't contribute to PCM. Then why can't we do it the other way? Well, we saw 2 slides ago. If we first start by updating this particular reference to now point to the new node, this one no longer exists. So how do we actually figure out how we're supposed to update the next reference of our new node? Right? What value do we assign to that to be able to actually have it point to that tail? Because, okay, in this case, great, it's a tail, we have a reference to it. but in any other case, we wouldn't have a reference to it. And in fact, how do we even know it's the tail? We simply pass you a node and say insert a node with a new element after this node. All right, so we have to do it in that order, so we're able to do that. How do we reverse the list? We did discuss that. We don't need to do that for this prac. Extend the due date to tomorrow if it's not marked. Know that we're getting you used to doing this within the time that you have, but just like last week, you will have an additional hour within which to do it. All right, so if we follow that method where first we update the reference of our new node, then we update the next reference of the node that it must be inserted after to now point to our new node, it fits in perfectly. All right, all our references are now correct. Yes, well, we could have asked for you to insert it after the head, but it's after any node. This should work for any node. So we wouldn't just say insert a new node anywhere randomly. Remember, our list methods were insert first, insert last, insert after, insert before. All right, so you're going to be implementing those. However, I'm not going to ask you to implement insert first or insert last because the answers for those are within the text. Again, remember that you should be drawing, right, in some way designing what it is you're trying to do before you go ahead and implement it. So even if you have the correct lines of code, if you don't do it in the correct order, like we just discussed now, you may not get the desired outcome. So please, before you even get started, spend a little time thinking about what each method is supposed to achieve. Write out whether it's going to be using a diagram or pseudocode, what it is that you want to do, then start its implementation. If you try to implement whilst you're coming up with the algorithm, it becomes a lot more difficult. So please let's remember that. Design should be 40% of our entire process, including 20% of the time implementation and 40% testing. All right, so these are simply linked methods that we're going to ask you to implement. Previous, which given a node, return the node that occurs just before that given node. Replace, so given a node or a new item, replace the old item that was in that node with this new item and return that old item. Insert after, given a node, insert a node right after it. That's very simple. We just went through the steps for that. Insert before, a little more difficult. You don't have a reference to the previous node, but you have to somehow get that reference to be able to insert after that node before. Okay, so I've already kind of given it away. If you knew what the previous node was, you could insert after that to be able to insert before the current node. If you've implemented previous, then it would be straightforward. You could call previous, that gives you the node that occurs in the list just before the given node, and you're then able to use that to insert just before the given node. All right, then remove. So we give you a node, we want you to remove it from the list. Again, you would have to actually know which node comes before that to be able to work that node out of the list. So you have to link hop to be able to remove a node from our list. Search, well, that's straightforward. Traverse the list, searching a particular item. When you find it, return the node that contains that item. So return a reference to the node that contains that item. And then toString, return a string representation of the singly linked list. You'll note that we've given you a toString method for the type of element that we want you to work with for your node object. So you simply have to use that to now create a string representation of the singly linked list. All right. Then within the main class, you have to be able to write part items to a file, so to write objects to a file, and you have to be able to read part items from a file. And in fact, let me just say this so we don't have any problems when you're going into it. Note that these methods, insert after, insert before, should work for any node within my list. So you can't assume that there'll always be something before and after. The way that you implement your insert before should work even for the head. So even for the head node. Insert after should work for everything up to and including the tail node. So just note there are some cases you have to make adjustments for to make sure it works for everything. Then write part items to file and read part items to file. Let me say this, and please do adhere to it. I know there are many ways that you can do this. You can go and simply Google it, look it up. Rather, go look at your notes. If you haven't looked at your notes for object input and output, go look at your notes from last year and compile for yourself a strategy to do this that you can use at any time. As I already said in Discord, and one student asked, you should be able to read and write to and from text files, binary files, and for binary files, that's byte by byte or objects. You should be able to do all those things that you learned last year. So you can have notes for yourselves for those. You have the advantage that you're working remotely, but rather than simply Googling it and doing it in a way that you don't understand or you're not going to be able to reproduce again, rather make notes for yourself so you can do it in a systematic way. And the easiest way to do that is the way that you were taught last year. So if you still remember that, then follow that procedure. And these notes are from those slides. Remember that we use object input stream, object output stream to serialize and deserialize objects to read and write them. And of course, that assumes that that object is serializable. So that object has to implement this type serializable. Note that doesn't actually enforce any particular methods, so it's more that you are marking it as serializable. So check that you're trying to write something that is serializable. All right, so some questions. Fact doesn't count. It isn't counted towards your PCM, that has been said already. If we understand it can reproduce away from Google, that's okay. All right, but I would assume that what you've learned in second year, you've done, you've practiced, and you understand. So random access file is not okay to use. No, you should be reading it in the order that you've written it to the file. All right, so just wait 1 moment. I'm going to log on a different machine so we can take a look at the code. So please don't type any questions for the next minute because I won't be able to see them as I switch to the other machine. All right, there, finally. There's just an issue with the audio there, but let me open Eclipse and share that with you. All right, so assuming that you have extracted your source folder there, you will have a bunch of files within there. I have increased the font as requested last week, so hopefully you can see that a little better, I hope. All right, so let's begin with the interface list. This should be familiar to us. This is what we agreed defines a list, the list ADT, that it should have this behavior. Should be able to add after a given node a new node with this item, add before, add first, add last, no remove, so to remove a particular node from our list and to return the element that was stored there, that's a type T, to search through a list and return the node that contains the element that we're given here, first, and a few others. All right, so let's take a look, and of course the helper methods is empty and size. So within our single linked list, you have to implement all of those and a few others. I have not, or rather I've already given the implementations for the ones that that you already have in the text. It does you no good to go and simply copy those from the text. And so instead, it's the ones that aren't in the text and the ones and a couple of new ones. So the first one isn't in the text you need to implement is previous. So given a node, given a reference to a node, you should return the node that occurs just before that node within the linked list. That does mean you will have to link hop from the first node, and each time looking at, well, what's the next node? Once the next node is equal to the node that we're looking for, then your current node is the node that you should return. Next, I've given you a petition of that because that's nice and easy. Replace. That's just for a single mark, because given a reference to a node, you should be able to simply access the element stored at that node and change it to this new element item. Insert after, given a reference to a node, insert a new node with this given item after that node. That's straightforward. Insert before could be difficult, but if you have previous, if you have the method that can return the previous node, the node just before this node, then that doesn't require any work. You simply get that reference and you can add after that to be able to insert before this particular node. All right, first and last is given within the text. I've already given you invitation for that. Just note that you do have to adhere to, or rather, all these methods should work for all the nodes in our list. So make sure that when you're trying to insert before, that it has to work for the head node as well. Remove will give you a reference to a node. We want you to remove that node. If this were a doubly linked list, that would be straightforward. Simply change the references to this node contained within the previous node and the next node. However, this isn't a doubly linked list, so again, you need a reference to the previous node to be able to work this node out of the list. All right? If you've implemented previous correctly, this shouldn't be an effort. Then search element, find a node that has this element within it and return that node. Is empty and size are given to you because those are already within the text. Then we want you to create a toString method. So we give you just an empty string there. You start at the head, at the end you should return the result, and that result should contain all the nodes within our single linked list in this fashion. So the element of each node within parentheses, then we have a little in-between character there, in between characters, then the next element, and the next element, and the next element. Just note that the node class already has some toString method, so you can call that within the single linked list toString method to create this format that we've given you here. All right, so questions on that? Yeah, I see that there's an issue with that interface. I will add those, just update it. I think there's an older version of it by mistake. Yes. All right, it should have our previous first and those, okay, I'll simply find the version that is correct and update that. Or you can just add them here, right? Doesn't make a big difference. Then main. So you've been given a program that already does the work for you. However, it does require you to be able to read objects from a file and write objects to a file. So there are two methods you should implement. One that writes all the objects that are in our linked list to a file, and one that reads them from a file. Right? What type are there? It's a custom type called product item that has already been given to you. You have to really worry about that and note that it is serializable, so I can write it to a file. Right. And as I said, for these two, it's not new work. Rather, I want you to go and remind yourself how to do these things, so that you'll be able to do them subsequent practicals. All right, are there any questions about what's required of you for this practical? Okay, and while you type in those questions, I'll just update that interface to be correct, the correct one. All right, so that has been updated to the correct one. Then questions. Not just the interface, it's slist. Well, slist will give you errors if you are trying to override methods that don't actually exist within the interface. That's why it gives you those errors. Okay, so with the correct interface, then that should be fine. Let me update the interface just within Eclipse, so we'll see that that does indeed work. Okay, hold on. Yeah, this is the correct one. If we save that, and save that. Oh, that's strange. Doesn't even seem to. All right, let me remove this. Okay, I'll use the very one that I've downloaded from Eve just to ensure that that is the correct one. Okay, yes, that does work. For some reason, Eclipse isn't happy when you change one of the source files directly there. All right, so you'll see the only errors now are those about having to have certain return types. We could just add a return statement, our usual null, and that would work. All right, but of course, you should actually put in some useful return statements within that. Okay, that's tested. It does work. As usual, you have, can I see a question, Pratt? Because changes were made. Oh, okay, I guess you're telling someone else that they should go and update that. Yes, using to the J. Right, so any questions regarding the prac itself? If you wanted to set the path for the file to be saved in a different location, by default, the current working directory, so wherever the code that you're executing is, then the file should be created and stored there. If we change the path, then we should be able to create a file or read a file anywhere else. Yes, the new source of file is up. Okay, they should be on Discord. I will check now. But all the systems should be on Discord for this period. If there is an issue, then I will just contact them and remind them to be there now. All right, so there don't seem to be questions about that. So we'll stop the lecture there. I will be available on Discord until the end of the session, but as usual, you'll have that additional hour after that within which to upload that. To receive a test.stat file, well, the idea is that if you do your write method correctly, it'll create a file, and you should be able to then read a file, be able to read that file. All right, but I guess you want to test each method individually. You don't want to start with the write file. You want to start with the read one. Then I will just run the program, create one, and add that as an additional file again. Actually, that won't be in the zip file, so just as a separate file with an additional file.